तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We saw earlier a realization of simple design using 2 input and gate, and we have also seen the test bench with nomenclatures different here. For A input, it is same as the design A input, whereas in is actually connected to the B of the design, and similarly Y of the design, that is the output, is connected to the out here as far as the test bench is concerned. We have also seen the design module as such, and the core statement is assign statement with A and B ANDed and assigned to Y, that we have already seen. And so this we can see it. I mean, we have also seen after invoking the model sim, and the waveform are quite difficult for you to view, so we have done it on Paint. Although you won't see live as such, it is an actual capture, and we will see it right now in this. So again, this is basically from the wave which we have seen after invoking model sim, and we will also invoke it once again, and it has been pasted in the Paint, and that's why you can see readability is far enhanced now. So you see that A and in are the two. I hope you can read this on the TV monitor. And A and in are the 2 inputs of the test bench, and out is the final output. And this corresponds to A and B inputs of design, and Y output corresponds to the out. So here on the right you see the actual waveform. So just remember A and in are the first two are the inputs, and last one is the output, what you see here. And you can also see at the bottom time in nanosecond. Remember that we had 20 nanosecond displaced at every point of time. For example, in this we have seen the test bench here. So we have seen that after 0 it is 20, 40 and so on. So what you have here is precisely the same. Here 20, 40 and so on. And actually second division is 20, just remember that. And let us go to the different inputs. See, in the test bench, the two inputs are A and N. this is 0 level and this is 1 level here. So again for in input, this is 0 up to 20 nanosecond, and next 20 nanosecond it is 1. So the combination that you have as per the truth table that we have seen earlier for this test bench is 0 0. So corresponding to 0 0, this is an AND gate, so you expect 0 as the output, and that is precisely what you have here. This is 0 level, and you also see here the exact state, and since we cannot see it live, if you click here, this also will change, but here it won't change because we have only captured earlier, and it is rather static, it can't go dynamically right here. And so if I click here, I will be getting the same input that you see here. For example, it will be 0 here and 0 here. So the moment I click here, these two will get transformed as 0 0, and so is the case anywhere. It will reflect the point at which you have clicked. Whatever is the logic level at that point of time, it would reflect there. And you can see 0 0 combination. Next is 0 1 here, and corresponding output is still 0 because it's an AND gate. AND is a simple multiply like thing in a binary. And next is you have 1 0 for that A and in, and for that also will give you only 0. So this is the AND gate, this is the output. And right for all the three combinations you have only 0 here, and it goes to 1 when the last combination 1 1 is encountered. That's what is here. And another thing that you would notice is, just remember this waveform. You don't have to remember, you can physically see. This is nothing but A, and the same waveform appears here also. So this corresponds to the design, whereas this corresponds to the test bench. Now I hope it is clear that whatever connection we have made at the test bench and design is precisely the same, and that's what you get here. So what you have seen is A and input or corresponding inputs in design A and B. So B must be the same waveform as in here, and similarly the out must correspond to Y output here now the design. So these two must correspond. So that is this and this. So it is same precisely here, and you can see here too. So right here, and these are all the two outputs. So this is nothing but what you have seen here in test bench. So this is precisely what you have got right now. The timing diagram that you have seen is precisely the same. So A, B exactly in the same order. Okay. So now let us move on to the next one more thing we have mentioned in this. This is the test bench applying different at different points of time. We have seen that at the test bench gets the very same waveform as you have in design. Only then you will get a feel that what you have really connected really appears on the top level. Test bench is always the top level. At least for once you should verify that it is actually reflecting the design wherever you have connected. Once you have done, there is no need for you to do it every time. So just to get a feel, make you feel for it, I mentioned that. So we have seen that at every 20 units of time, you see all are precisely 20 units of time. And earlier a question was asked whether we can have it cumulative. It was cumulative as far as the times are concerned. Instead of 20, etc., you had 20, 30, actual time reflection, and using a non-blocking statement as such. That is less or equal to, instead of this, you use less or equal to here, and then put this 20 before 0. So at that point of time only this will be assigned there. And if you had given 21 here, let us say, then at 21 nanosecond only this will be assigned, and so on. And we have also seen earlier that what will happen if you there was a time scale here. So we saw that 1 nanoseconds is the time base, and you have marking in steps of say 20, the major marking as such. So 20 into 1 nanosecond is 20 nanosecond. And what about this? This is 0.1 nanosecond. So you can even specify here, instead of 20, you can specify say 20.3 or something like that. So you can have in steps of 0.1. So what will happen if you specify 20.35? What is your guess? What should it be? So I will answer that. So it will round off to the next higher value. So 20.35 will be rounded off to 20.4, and that is precise. If you here had you commented those statements which has only this 20.35 etc. specified, then what will happen and run the code in simulator, you will get the waveforms like this. So you notice that. So at the bottom different timings are mentioned. It is precisely the same as far as the function is concerned. It is exactly the same except for slight difference here. You notice that here this is happening, this transition is happening. See, the output is this is the output. Input transition is happening at 20.35. It has been set in the original file. So what will happen here? Let us see what it reports. See, just see here, 20,400. That means it is reporting it as 20.4 nanosecond. So 20.35 has been rounded off to 20.4. That's what it means. Another thing that you see here is you have also you can set as many cursors that you want here. For example, you want to measure the time interval between one point of time. For example, from this to this next transition, how much time it has taken. What you can do is just make a cursor, which we'll be seeing in the model sim. Although the visibility will be poor, I'll explain on that. And you can click the cursor here and then say add the cursor. Then this dotted cursor will be put on that point of time. And you can see once again the next transition also is staggered, because the very first thing was 20.35. Thereafter it was maintained as 20 nanoseconds. So it's a relative thing. So automatically everything will be displaced by that 20.35. Actually in this system will interpret as 20.4. And mind you, all these timings are don't appear in synthesis, because in the design you are not supposed to give any timing as such. This is exclusively for simulation as such. So otherwise the functional aspects are all precisely the same throughout. You can see one more here, and actual cursor is right here, and once again there is a marking here. It marks the interval between this cursor and this cursor. That is how we can find out the rise time, fall time of wave and so on, if there is ringing. But it will reflect only after back annotation as such, and not at this stage. And having done this one, we will invoke the model sim and then go on to the combination circuits design as such. So we invoke the model sim here. And let us create a project. So this is the project location. So and you have to give a project name. Let us say it's a combination circuit. So we'll give it as com circuits. And there it must be in work directory as such. So what it says is a project by the same name is already existing. So it's asking whether it should overwrite. You just answer yes. So now what there is one thing called library here, and it must be in work directory before you start compiling, loading the design and so on. So let us now let us see where we are here. We have opened the model sim, and then using that open project, and here it's already the combination circuits project is already there, and we are right there. You can just give pwd here in the command mode, and then make sure that we are in duser ram dvlsi design etc. This is the directory that we have all our files. And if you want to view all the files in this particular directory, just type directory in this prompt here, model sim prompt. So it lists all this. It may be difficult for you to read. I'll just read out. So we have combinational underscore circuits.v, and then combinational underscore circuits underscore test.v. This is what we have already seen earlier, and we'll be seeing again, and this is what we are going to simulate. So in order to do, before we simulate, we had to do the compilation that we have already seen in the flowchart that we had considered earlier. And now let us compile that and design, then compile. Then you see here combination circuits underscore test. Since we have included the design, there is no need for you to mention specifically all the lower modules. So it is enough if you just compile the test bench as such. Double click here, it will automatically start the compilation, which you can see on this window. And I'll just double click here on this file. So it has compiled the combination circuits, that is a lower module first, that is the design here, and then followed by the test bench here. And once you have done, there are no errors. And later on we will deliberately create errors and see how the compiler functions later on. And right now we will have a smooth flow over our simulation. And once you have finished with compilation, you are done with it. So you just dismiss off that window. And then next step is to load the design. And what you have compiled will have to be loaded. So it opens another window with a design load design we have seen. It opens this load design window, and you once again the module of interest is combination circuits underscore test, that is the test bench. Double click here, or you can just say single click and then say add here and then say load. So let us see if there are any errors. Again it will point out even during loading time. What compiler is unable to track the errors, this loading may do it. And later on we will see by injecting deliberately. And right now we are ready for viewing the waveform. So you use view and then signals, click on the signals here, and then it opens the signals window, and in this you see view, and with view what you have is wave, and then go on to the last option called signals in design. And when you click on that, the waveform is opened. And you don't require signals, so you can dismiss off that window. And now this is the waveform window. Right now it is blank. So if you run this one, you notice that you have all this listed. Unfortunately, you will not be in a position to view that here, and that is the reason why we are copying from this into Paint and later on displaying, which will be using the same technique even here. So just listen to my words, then you will you can make a guess as to what you are looking at. So right here you see A, B, C. These are all the select pins. If you remember, in combination circuits we had used for mux selection, and on 8 input mux also we use. So I0 to I7, these are the signals. And then we had a magnitude comparator comparing two numbers as such, and these are the N1 and N2 for that. And it's basically then one more small design was there which computed the sum, and then if greater or less, more or less combination when compared to a preset value is encountered, it sets the output, sum output, which will be there listed elsewhere. And similarly we have also seen so many outputs such as F1, F2 and so on. They are all listed here. So let us, and here in this column right now it says XX because the simulator is not run as it. And in order to run, we'll just see what commands are there. And we have some lens here. It is something zooming in here. If you press this one, you can zoom in. And before that, let us get the waveform. Then we can do all this. So if you see here, restart. If you want to restart the simulation, and straight away we will go for run all. What will happen if you give run all? So I had click on the run all. You see a waveform pattern here, and it has also opened your combinational circuits underscore test. That's the test bench.v, and you can see that it has stopped at last statement called the stop, right? And I'm afraid you will not be in a position to read this once again. Anyway, we have the actual bloated up combination circuits file here. We'll see that later. Now that we don't need this .v file, we'll remove that window. Now you see waveform here. We can improve this view by pressing this. So this is the thing you see here. That is third, fourth one, and this is for zoom full. So the entire vision is had here as far as that functionality is concerned. And now you see so many activity all around here, and these are all corresponding to I0 through I7 and so on. In fact, activity is found everywhere, and still it is small. So what you can do is you can just increase this and keep increasing using that plus, or if you say minus, you can decrease it. And all this will be very difficult for you to find. We'll open a particular functionality as such and then describe that. And there are more controls here. You can, as I said, you can create a cursor here. You can just click anywhere. A cursor cursor appears, and this is at 80 nanosecond. These are all graduated in 2040, as you have seen in one of the AND gate realization later. Earlier. It is precisely the same here, and you can go from let us say this we had selected one of the signals called I2, and wherever there is a transition occurring at I1, I2, we can go there by pressing this arrow here. See, for example, it has gone to a negative transition of that I2 here, and one more time you click on the left arrow, it goes to the positive transition. Like that you can go for any other signal. Suppose I have more than one or two signal, you can just say let us see, we will use the other arrow this time. So it has gone to negative of transition of the I2, and with this it has gone to negative transition of I3. Maybe we'll have to find out why it did not go to this. So you'll have to experiment with it and get a feel of the tool as such. This basic thing that you can just utilize for your benefit, going from one transition to another. Say, suppose you want a cursor to be added. You have here, there's a cursor here. So if you say add cursor, it has added a dotted line here. It had, I hope you are able to view. No, it won't be possible, but it is possible in the paint shop image. That is the difficulty here. And the cursor has moved here. Suppose I want to put, let us see what happens. Right? If you move this one, that dotted line cursor has moved to the previous position. So you had to make some iteration. It is maybe we have not understood rightly the tool, or there's a bug in the tool. It doesn't freeze at that point. Say, you may have to make a couple of attempts. Let us see here. We make it here. It has made cursor right at that point. Right? Now let us transfer it here. So there's no longer any cursor, but earlier thing also has been marked. And if you want to remove a cursor, let us say this. So it has removed this. This cursor has been removed. So last in, first out, something like that. You have to experiment around that. This is not a very important thing. You can just play around and find out, discover. And now let us go to the functionality as such. So major things we have already covered, and more will be covered a little later, and or in the subsequent lectures. So now let us see the first thing that we have. We will go to the this is combination circuits that we have had. So we have seen that so many inputs listed here. We will straight away go to the actual functionality where we have put the assign statements, etc. So the first assign statement is here, and we have also it is much simpler to view this PowerPoint here. So we have seen buffer, inverter, and OR. So this F1 through F4, we have this functionality. Let us first view this waveform, and which has been got into the paint, and that particular thing is being opened right now. So what you see here is A and B and F1 to F1, F2, F3, F4. Remember that F1 is nothing more than a buffer. So buffer of A signal. So whatever is the A signal you should get in F1, and F2 is just inverted signal of A. So let us just remember these two and see. The third column is the F1 and F2 is the fourth one. First two are A and B inputs. So just remember here, and again once again the time element is there here. And if you remember, we have given 25 nanoseconds at one point of time. That is what is marked there, but it's not of much concern right now. So just to show, the cursor can be placed anywhere. So this is the cursor that you had seen. And going to the two inputs, so what it does is, this is A, and it is in fact 0 all through, and corresponding output which is buffered thing is also 0 here, you can see here. And now it just follows the input here, because this is the output for the buffered. So whatever is the input, you have precisely same here. And next is inverter. This is till the end it is same. And next is F2 is inverter, as we have seen here. This is PowerPoint. So next one is the inverter. A is inverted and assigned to F2, and next two also we will just remember, and OR, so of AB. And going to this once again. So all marked by black are outputs here. So A, B only are the two inputs. So you can very easily remember, and where we make the transition we can find out from here also. See, this is 0 here, this is 0. And now what we are looking for is second output, which is inversion of the A. So what is happening here? See, you can recognize from this is high, that is here, because it is low here, it has this is the inversion of that signal. So it is high here, that's what you want. And when it when the input goes high, it goes low, because it is an inverter. So you have thus checked the functionality of inverter as such. Next we will check A and B as such. So that is the third one. F3 is the ANDing of the two inputs AB. So AB are the top ones here. So right now you see 0 0 condition here. For all 0 0 condition you naturally expect 0 here. And for 0 1 or 1 0, that also will be 0. That's why it is continuing at low here, right up to this point. Here also 1 0 also is 0 here. And now up to this it is same 1 0, this 1 0 here, and now here it is 1 1. So at that precisely at that point of time it goes high here. So this is AND gate here, and similarly OR gate. OR gate is F4 and OR with A and B. So again 0 plus 0 is 0 here, and then 0 plus 1 is 1 here, and it continues to be 1 because 0 1 or 1 0 or 1 1 are all basically 1 result. So it is continuing to be 1 here right from that. So we have seen the functionality of first four outputs. Similarly we can see the second one. So here the second one is NAND, NOR, exclusive OR, exclusive NOR as such. So here this is F5, F8. NAND, NOR, exclusive OR, exclusive NOR with AB as inputs. So we will just see where we are. So AB once again is in this here. This is F5 to F8, and these are NAND, NOR, exclusive OR, exclusive NOR. And see, in this case the first output is this NAND. So this is 0. So 0 into anything is 0. So NAND means not AND. So that means not 0. So 1. There should be an inversion. So this is 1 here. And here also 0 1. So again 0, not 0 is 1. So here 1 0. So it 1 will continue here. Here right up to that 1. Then it becomes 0 because both are 1. So 1 into 1 is 1, and then not 1 is 0. So you have verified NAND here, and this is NOR, F66 NOR, and that is this waveform here. And you can just see here 0 0, not 0 is 1, and then 0 1 is 1, not 1 is 0, and that will be the same case here all through, right, for rest, because R is basic R is 1 for all other combination. And we have verified NAND and NOR, and we will verify the exclusive OR as F7 is F7 and F8 are exclusive OR. And here it is 0 0 combination as input here, and you have 0 for exclusive OR, and exclusive OR it is inversion of that 1. So we can just see together. And next is 0 plus 1 here in this region, and that is 0 and then 1. So 0 plus 1 produces 1 there, and not 1 is 0 here. And here also 1 0 also produces 1. It is same as OR gate except for the last combination. And that's why you have 1 plus 0 is 1, and that's what is 1 here. And this is exclusive NAND, NOR. And for this case, it is 1 1. In 1 1 case, exclusive OR is 1 plus 1 0. So actually the sum is first bit is 0. So you need, we are looking at only the sum, not the carry, and that is what is here. It is 0. 1 plus 1 is 0 in exclusive OR, and inversion of that one is exclusive OR, which is 1 here. And we have checked up to F8 here, so we will remove this window. And next one is that's what we have used always statement in this next thing, and made a majority logic as such, AB plus BC plus CA, and 3 inputs here, and then concatenation also. So A, B, C put in the same order. So we will see both here. This is F9. First we will see that F9 to F12. And once again A, B, C are the inputs here. And what it does, you can see the assign statements also. So that's what we have already seen here. Always statement is here. This is what we are going to see here. It's AB plus BC plus CA, then ABC as such. And so F9 is nothing but AB plus BC plus CA. So first 3 are ABC. Just have a look. This is 0, 0, 0. All of them are 0. It is going to be in binary progression. 0, 0, 1, then 0, 1, 0, and so on. In a binary progression it is going. And so that is what you have here, first output. So here, what is happening here is AB plus BC plus CA, note that it is only a majority logic. So 2 or more number of 1 entries in the ABC will produce 1 output. For example, here, this, 000 here, and then 001, right? So, and here 100. So all this should necessarily produce only 0, because maximum number of 1s are 1 only, right? And beyond this, here you have 0, then 1, 1. So 2 1s are encountered, so it goes high. That's what majority logic is. That is here. Here. And again here, it is 1 0 0. So only 1 1 entry is there. So it goes to 0 here. And again here, it is a 1 0 1. So 2 1s are there, it's going high. And beyond this, it will be high because it is either 2 or even 3. For example, 1 1, and so it produces this, right? So it is 1 1 0. So it continues to be 1, and here it is 1 1 and 1. So 2 or more number of 1s will produce 1 output. So thus we have verified the functionality of this majority logic. And the second one is, that was F9. Next one is F10. What is F10? It's a concatenation we have seen of ABC, right? So ABC is precisely this. So it is in arithmetic progression, we can say, in binary progression, right? 0 0 0 0 0 1 and so on. So you should get precisely the same progression right here if you view this output. So that is what you see here, 0 0 0 0 0 1 0 1 0, because it is concatenation. Note that the first 0 on the left is A. That's what we had here. This, see, this is A, and the LSB is C. That's what we had here, and that's what you see here, and it is all in just arithmetic progression. So 0 1 1 1 0 0 1 0 1 1 1 0, finally 1 1 1. That's the end. And next is, I mean, there are two more outputs. What is F11? We'll see here. So it is nothing, F10, F11 is there, and F10 is the input. This right shift register as such, and it shifts by 1 bit, and there is also a left bit by 2 bits here, and we have seen earlier this source is F10 for both the cases, and whereas the output is F11 and F12. So F11 happens to be those ABC. It's basically what we have here, and A being the MSB here. So when you shift right by 1 bit, what will happen for F11 we had to see. Similarly for F12, but in this case 2 bit shift as such. So let us see that once again. So that is F11 is right shift by 1 bit. So what should be shifted? It is actually F10 which is being shifted. That is the input we have seen. So let us see what happens here. If you right shift here, this 0 will get lost, and vacated bit 0 will always be filled. So it continues to be 0. So that's why the result is 0 here. And again the input is now in this case 0 0 1, and if you right shift here, what will happen? This 1 gets dropped, and 0 fills the MSB. So you continue to have only 3 zeros. That's why it is all same. Now you see the difference. 0 1 0, if you right shift by 1 bit, this 0 will get dropped. So what 0 will get filled on the MSB. So what you get is 0 0 1. That's what you have here. And you can straight away explain in the same manner all this. So you can just see here. See what is happening here. 1 0 0. When you shift here, this 1 0 shifts here. Similarly, this 1 0 continues to be here. So this 1 will go to the last bit. MSB again filled here. And now the last one is 2 bits left shift here. So we started with F10. Remember, this is F10. So when you shift left, it appears to be same here. 2 bits now we have to shift. Now let us see this. See, if you shift 2 bits, this 1 will go to this position first bit, first shift, and second shift it will go here. And bits vacated will be filled by zeros. So this it will be 1 0 0. That is what you have here. So you can inspect every other combination. For example, this one 2 bit shift, so 1 is lost, so it becomes 0 here. And again this 0 1 will get dropped, and only this one will survive here, and so on. So you can reason out very easily. So finally you can see this 1 1. 2 bits, this 1, 2 ones get dropped, and what remains is only 1, and 2 bits vacated are zeros here. So this will complete up to F1 through F12 of the combination circuit. And next we have seen mux there, 2 input mux here, and that's what we are going to show here. So in mux, what we have 2 inputs I0 and I1. And there's a select control A, and mux2 is the final output. And the assign statement which did this operation was when A equal to 1, then select I1 and then output it to mux2 as such. And otherwise you take I0 as mux2. And this is precisely what we have here in this final output as such. And here A is the select control, I0, I1, and mux2 is the output that we have already seen just now. And we will see, remember A is, I0 is the one which will be assigned. If A equal to 0, that is what is here, you can see this is 1, this is 0. So all through it is 0 here as far as A input is concerned, which is select input. And here, what you have here is I0 input as such. So we have, this is the input that we are simulating. and through test bench we are simulating, which we have already seen here, and every 10 nanosecond we made it to 1 and then made it 0 and so on in the test bench. So I0 and I1, just have a look. I0 is applied here and I1 is applied here. Now let us see, output must reflect either I0 or I1 depending upon the select control A, and here this A is 0 here in this position, and that means we are going to select I0, not the I1. I1 will be selected only if A is 1. So whatever is the input waveform here, this must appear at the output. That's precisely we have here, right at the bottom. You can see here, right? And beyond this, it is continuing to be 0 as far as A is concerned. Therefore, this pulse being low here, beyond this, it continues to be low here. Now what is happening? One unfortunate thing here is I should have made this 1 here, but if I make it here for other examples, you can't see clearly. So this being a simpler case, I thought I'll sacrifice here and show you that waveform in the next subsequent things, which will be a little more elaborate than this. So what is happening here, since A is 0 all through, what you see at the output is I0 only again, because I0 is 0 here, you see only 0, and this waveform is not coming. That's what we have explained just now. And now this waveform will be taken into account beyond this, but you can't see unless the pulse was here. I could have written the pulse here or made the other way around, and this you will be seeing in the next example. Next example was to configure MUX4, that is this. So here I0 through I3 are all the inputs now, and BC are the select pins here, and MUX4 is the final output. B is the MSB here, and we'll see the waveform corresponding to MUX2 and see that all the patterns are intact for this, right? We are trying to use, no matter what outputs are created, we are trying to use very same inputs ABC repeatedly we use, right? Because in the actual application design, all these designs will be interconnected. Some of them will be used for some other purpose, and very rarely few outputs will be energized and not utilized inside. And this combination circuits or sequential circuits, although we have put together all different simpler modules, they are not the total project as such. It is piecemeal thing, but it gives an appearance as if it is a total project. So a total project, application project is not much different from this. So it is only to illustrate the, demonstrate the actual simulation that we have put it together here. And now let us see this MUX4 whether it works. And in one shot we can find out. See, BC is the input here. It's once again in binary progression, 0, 0 here up to this. This is 20 nanosecond. All waveforms are marked by 20, 40, 60. And so here it is 0, 0 here, then 0, 1, 1, 0, 1, 1. So 4 combinations only are there because BC are only 4 combinations, right? 2 bits means 2 to the power of 2. 4 combinations only are there. So now let us say for 0, 0, if this is select pin for the MUX, 4 input MUX. So naturally there are 4 inputs are I0 through I3 here. And I0 is the very first thing. It corresponds to BC being 0, 0. For 0, 0 input, I0 must be selected. That means to say this MUX4 output, if you view them, it should be very same as I0, and you can precisely see that to be the case. See the very same waveform here, and no other waveforms are there in any other inputs. So you can very easily infer that this MUX4 is clearly due to the input I0 here. That's precisely what you have here. And in the next, when BC changes to 0, 1, so what you have is I1 appearing here. You can just see here. And mind you, it happens right at this stroke of change. C is changing here. Right at that point of time, it switches to the second input. So what you see right from here till the end is precisely the I1 signal here. That's what you see here. And so is the case for I2 here, which appears here. So you get the output corresponding to that. And finally for the last one, this is I3 as such, and this is corresponding to B and C being 1 1. You can see this is 1 and this is 1. So we have seen 2 input mux and 4 input mux, and we will see 8 input mux also. Now we will see mux. So in 8 input mux, what you have is you need how many controls totally? Okay, this being a large waveform, it has been split into 2 here, and unfortunately this ABC appears only in the second waveform as such, but it's not a difficult thing to remember because we go only by the binary progression as such here. Only thing is, remember the pulse for a particular input has been created at 10 nanoseconds, and interval is 20 nanoseconds, something like that, right? And now the time base has been changed in order to accommodate all the combination possible. That's why it is time base is different anyway. So what matters is the actual waveform, whether it is appearing. In fact, you can see the wave here. This is mux 8 here. Depending upon ABC, if it is 0 0 1 0 0 condition, that is here, so you should get the mux 8 input from I0. Let us see whether I0 is pulsed there, and you won't get it here because it is there in the previous one, that is in this. Say I0 is pulsed here, I1 is pulsed here, it is all subsequent, so you don't have to go back to this file again. You can see every time it happens, say all through, and I4 up to I5. It is all sequential, that up to here. So in the same order it goes. So we will just see in the next file, and here also I6, where does it go? This completed in, so this waveform came beyond 100 nanosecond. Just remember, this is corresponding to I5. So in this you have I6, it must be somewhere, it's coming here, right? And that is precisely what you have here at the output here. Say mux 8. So this was the very first pulse of I0, then I1. So that is precisely what you are having here. All right. And ABC are the selector inputs. Anyway, and you can see, for example, these are all ABC 111, 110 here. So 110 should have given. So 120 or something, we had this I5 there. So this must be I6, which belongs to this precise input condition. Let us see whether there is any, right? I think this is the one, right? Oh, that is the one. This is I6, right? So this was that I5, and I7 is the last thing. This is corresponding to this. Here in test bench, I would have forgotten to make it low, so it remains high. That's how. So you can, corresponding to this, A, B, C are all 1. Okay, thank you.